When it comes to complex numbers, it's very important you understand and know how to use the modulus correctly. This is something that's very similar to an idea in real numbers, but now is used within the context of complex numbers. So today, I'm going to teach you all about it and then some. This is Complex Numbers 101. In part 1 of Complex Numbers 101, we talked about everything involving the basics of complex numbers you needed to know. How to define a complex number, how to add them, the different laws that went into them, how to multiply, subtract them, etc. And you can find them all in part 1 if you want to see more. But for the purposes of today's video, we're going to talk about something called the modulus. And this is a very simple idea. This is known as the length of a complex number. So, if you were to pick a point where this is the real, this is the imaginary, we'll call these 1 and I, and you had a complex number which is 1 plus I, the length from the origin, 0, 0, to this point. Now, if you've seen a very clickbait one on YouTube, people would have thought you could use the normal Pythagorean theorem you used before with 1 and I. So you would get 1 squared plus I squared, which would be 1 minus 1, which is 0. But this is incorrect. So let's define specifically what the modulus is. So the modulus still is the length, but it doesn't actually involve I. So if we had a point here, that the real part was x and the imaginary part had a y, we'll put im here for imaginary. If you were to actually do its length in the real direction and its length in the imaginary direction, you would find that this is actually x and this is actually y. So the modulus of a complex number is the square root of x squared plus y squared. It does not involve I. So, previous one we showcased where if z was 1 plus I, in fact this would be x would be 1 and y would also be 1. So in fact this would be the square root of 2, which makes a lot more sense than 0. So that's a very simple idea behind the modulus. It has also another weird relation with another thing we do with complex numbers. Another thing we use with complex numbers is known as the conjugate. And this is the idea of we write our complex number here, I'll keep above that this is x plus I, y, and put a horizontal line above it. And what this basically means is that instead we're going to flip the sign between them. So we get x minus I times y. Now, visually, when it comes to complex numbers, all this is doing is basically saying if I have a point here, which is x plus I times y, the conjugate is now flipping it across the imaginary. So now you have z equals x minus I times y. It is just flipping it across the imaginary axis. However, it has a unique relationship with the modulus. So let's see what that's about. So if I take my original complex number and I multiply it by its conjugate, what do I end up getting? Well, I have x plus I times y plus x minus I times y. And using the same properties we did in part 1, we're going to use FOIL to multiply it out. So I'll get x squared, plus and minus here will cancel in the middle. And we will get minus I squared times y squared, which I squared is just minus 1, so we get x squared plus y squared. But this, as we just saw from our definition of the modulus, is the modulus squared. So the idea is that if you want the length of a particular complex number, you can multiply it by its conjugate and square root it to get its length. which is a very interesting thing to discover in the world of complex numbers. There are a few properties of the conjugate we need in order before we get to our final topic today. So, the conjugate has a few properties. If you have two complex numbers you're trying to add together and take their conjugate, it is the same as taking the conjugate of the first and adding the conjugate of the second. Second property is similar. If you were trying to subtract the two, it is the exact same. If you try to multiply two conjugate numbers together and take their modulus, it is the same as taking their modulus. It's the same as taking the conjugate of both of them and multiplying them together. And finally, the fourth property is if you take the modulus of 1, if you take the conjugate of z over w, it is the same as taking the conjugate of z over the conjugate of w. So in every single instance, the conjugate can always go in to the particular complex numbers that we have in it. Whether it's addition, subtraction, multiplication, or division, the conjugate always works through each of them. And we're going to use this property when we do our final topic for today. The final topic for today is the triangle inequality. And what it states is that if I take two complex numbers, that's called z and w, add them together and take their modulus, this is strictly less than or equal to the modulus of z plus the modulus of w. And we're going to use the conjugate to prove this. So the property involving the conjugate that we showed previously is that the modulus of any complex number squared is equal to the complex number times its conjugate. So now, let's use that same technique for our proof. So I take z plus w and square it. I will then get that this is z plus w times the conjugate of z plus w. Now from the properties of conjugates, this is now the same as the conjugate of z plus the conjugate of w. Multiplying them out, I will get z times the conjugate of z plus 2 times, plus z times the conjugate of w plus w times the conjugate of z plus w times the conjugate of w. And the first and last terms are the same as the modulus squared of both sides, plus the terms in the middle, which is plus z modulus w plus z plus the conjugate of w plus the conjugate of z times w. Okay, so the term in particular we want to look at is the 2 in the middle. So if I take z conjugate of w plus, and I take the conjugate of this is the same as saying z conjugate w. Now the idea is that if you are to take any conjugate and any complex number and add its conjugate to itself, remember that the conjugate is negating its imaginary part. So if I add these two together, I will get 2 times x, which means that if I add something plus its conjugate, I will get back that this is in fact equal to 2 times the real part of z and conjugate of w. For space, I've moved this up to the top, but bear with me as this is going to involve a few tricks involving complex numbers. So this one is less than or equal to, we're going to keep the modulus squared of z and w the same, and we're going to change the part in the middle to now where technically if you just take the real part, the modulus of that is always less than the total of it from this idea. So right now this is the modulus of z and w, and this is the real part of z and w. So we know from the hypotenuse that this always has to be greater. So this is greater than or equal to 2 times the modulus of z times the conjugate of w. Now that's our first trick. Our second one is going to be that, copying everything else down, the modulus of two vectors multiplied by each other is the same as taking the modulus of each vector and multiplying them by each other. So, finally, z squared plus 2 times the modulus of z. Again, the conjugate is just the negation in the y direction, which won't affect the length of it whatsoever, is the same as the modulus of w plus modulus of w squared. We can now finally, after all these steps, factor this to become the modulus of z plus the modulus of w squared. And at the end we will have that the modulus squared of z plus w is less than or equal to the modulus of z plus the modulus of w squared. So finally, we will have that the modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. And that is our proof of the triangle inequality for complex numbers. Like and subscribe if you want to see more. We do tons of topics on this channel. Feel free to comment if you want me to see another topic involving complex numbers or any other math topic you're looking for. Until next time.